Good morning. Today we'll discuss about the introduction to finite automata. So, so we'll discuss about finite automata and languages and basics of these topics. Finite automata. So, what is actually finite automata is? So, it is an abstract machine which is defined by a state diagram or state table. So, we'll see what is state table later. So, now we'll discuss about what is finite automata as a state diagram. So as a state diagram, it consists of states and transitions. So like it's like a graph. So which graph contains nodes and edges. So here nodes are states, and whereas edges are transitions. So so there will be a movement from one state to another state based on the input. So when you give an input to a particular state, it will move to another state. So it can be same state or next state. So a finite automata is also known as recognizer for regular language. So there is a let's take a language L. So it is called regular language if it is accepted by a finite automata. So there are two types of finite automata. One is deterministic finite automata and another one is non-deterministic finite automata. So deterministic finite automata or DFA in short. Uh, we can say that it is a DFA if it is in only one state at any given point of time. Okay, you take any instance of time, so it should be only one state. It cannot be in two states or more, two or more states. Whereas non-deterministic automata, it can be one state or more states. So that's why DFA is a subset of NFA. So you can say a DFA is also NFA, but not vice versa. So that means NFA can be in multiple states at the same time. Right. So this is a formal definition of deterministic finite automata. This deterministic finite automata is defined by five tuple. So it consists of five uh, elements like Q. So Q represents set of states. Sigma represents finite set of input symbols. Because from a state, if you give an input, then it will move to another state. So you need states and inputs, and out of all the states there should be one state, so from where we are starting, so that state is defined by q naught. And next, f. So a string is accepted by a finite automata if it reaches a particular state. So out of all states we can categorize them into set of final states and non-final states. So set of final states is defined by denoted by capital F. And next, transition function. So next, transition function, it is a mapping from a state q and input from sigma to another state. As I told earlier, in a graph there will be an edge from one node to another node. So that is from one state to another state by taking an input. The input is from sigma, so that's why the transition function is denoted by q by sigma implies q. So yeah, so DFA is a 5 tuple. So you need to explain all these things. So what is q, what is sigma, and all. Right. So right. So whether is why do we use DFA to recognize whether a language is regular or not? So what is language? Language is set of strings. So we'll take set of strings of that language and see whether it is acceptable by the DFA or not. So starting from the state q naught and taking the input symbols of the string one by one, and if we reach the final state after reading the last symbol, then we accept that string. So let's say there are three symbols. So we take first symbol on Q0 and then move to another state. Then take second symbol, then take third symbol. Like that, if we reach the final state after reading three symbols, then we accept that string. Otherwise, we reject that string. So if the finite automata accepts all such strings, then we say that language is regular language. Let L be a language recognized by an automata DFA A. Then L of A is called regular language. So there is a strong relationship between language and automata. So if the language is accepted by automata, then it is regular language. So a regular language, now we denote it as a L of A. L of A means L is language accepted by A, automata.